Today, we're going under the hood to look at the strategic engine that powers so much of modern finance and AI, NumPy. And we're going to see how one single design choice, how it manages computer memory, is the difference between a model that runs overnight and one that delivers the real-time insights you need to win.
So, let's start with a really critical question. What really separates a risk model that chugs along all night from one that spits out answers right now when you need them? You might think it's just about buying more servers, throwing more hardware at the problem. But the real answer? It's much deeper. It's a fundamental architectural choice, buried deep in the code.
And at the very heart of that choice are two different ways to store your data, a standard Python list and a NumPy array. Think of a Python list as your all-purpose, super flexible container. You can throw anything in there, numbers, text, all mixed together. But all that flexibility? It comes at a huge performance cost because the computer has to constantly check what kind of thing it's looking at. NumPy arrays, on the other hand, they're specialists. They have one strict rule. Everything inside must be the same data type. And in exchange for following that rule, they give you pure, blistering speed.
So where does this incredible speed actually come from? Well, it's not magic. The secret is all about architecture. It's about how these two structures physically organize data in your computer's memory.
And the key concept here is something called contiguous memory. All this means is that every single number in a NumPy array is stored right next to its neighbor, side by side in one continuous, unbroken block. Now, this might sound like a really minor technical detail, but trust me, it is the architectural decision that makes everything else possible.
Let's use an analogy here because it makes it really clear. A Python list is like a treasure hunt. Every item is stored somewhere else in memory, and the list just holds a series of clues or pointers telling you where to find the next one. To get through the list, your computer has to follow this winding path, chasing pointers for every single element. A NumPy array, though, is a perfectly straight road. Because everything is in one block, the computer can instantly calculate the exact address of any item. This lets the processor work miracles. It can grab huge chunks of data at once and even prefetch the next batch into its high-speed cache before you even ask for it. It's like a chef having every single ingredient lined up in order versus having to run to the pantry for each one.
And the impact on efficiency? It's just massive. When you're dealing with big numerical data sets, making the switch from lists to NumPy arrays can slash your memory usage by up to 86%. So it's not just faster, it's incredibly lean.
So here's the bottom line. That low-level, geeky detail about memory layout has a direct, high-level business impact. It is quite literally the bridge that gets you from slow, overnight batch processing to the fast, real-time analytics that give you a competitive edge. Now, having this amazing memory architecture isn't just about saving space. It's an enabler. It unlocks a whole set of what you could call computational superpowers. And the most important one of all is vectorization.
Just look at the difference. On the left, that's the old way of doing things. You write a for loop that goes through your prices one by one by one. It's slow because Python is interpreting every single step. But on the right, that's the NumPy way. That one clean line of code doesn't actually run in Python. It hands off the entire array and the operation to highly optimized, precompiled C code that runs directly on the metal. It's the difference between giving someone verbal step-by-step instructions and just handing them a perfectly engineered blueprint.
And vectorization gets even cooler with a feature called broadcasting. This is NumPy's incredibly elegant solution to a problem that comes up all the time in finance. What do you do when you need to combine two datasets that aren't the same shape? Like, say, applying one risk adjustment to an entire portfolio of assets. Well, instead of making you write complicated loops, NumPy just logically stretches the smaller array to match the bigger one, all without actually using any more memory. It's brilliant.
Here's a perfect example. Imagine array A is a matrix of two different assets and their values over 3 days, and array B is a single vector representing a risk adjustment for each of those days. With broadcasting, you can add that risk factor to both assets at the same time. NumPy sees that the number of columns match, and it just intelligently stretches array B downwards to perform the calculation. It's just insanely efficient.
Okay, so we've seen how it all works. But now let's get to the fun part, the what. How are these superpowers actually used to solve real, high-stakes financial problems? A huge part of risk management is sifting through massive amounts of data to find specific events. NumPy makes this trivial with a technique called Boolean masking. Here's how it works. First, you define a condition. You ask your data a question, like, which days had returns worse than -5%? Then NumPy creates a mask, which is just a new array full of true or false answers. And finally, you use that mask to instantly filter your original data, pulling out only the numbers where the answer was true.
And this is what it looks like. That one single beautiful line of code does everything. It asks the question and filters millions of data points in one shot. You can scan 20 years of market data for every single tail risk day instantly. This is what happens when you turn your logic into a vectorized operation.
Now, this is absolutely crucial, especially for anyone in a regulated industry like finance. How you filter your data can have huge consequences. See, if you use a simple slice to grab some data, NumPy gives you something called a view. It's super fast, no memory overhead. But, and this is a big but, if you change the data in that view, you are silently and permanently changing your original data too. That is a massive risk to data integrity. Boolean masking, on the other hand, always gives you a copy. It's a brand new, completely independent dataset. That makes it the safe and, frankly, the only choice for any kind of what-if analysis where you cannot risk corrupting your source of truth.
And for the quants out there, this is where NumPy becomes your best friend. Those complex formulas from finance textbooks, like calculating portfolio variance using weights and a covariance matrix, are the bedrock of modern portfolio theory. Without NumPy, you'd be writing horrible nested loops. With NumPy, it's a single line of code that executes blindingly fast matrix multiplication. It turns advanced financial theory into practical, real-time computation.
Okay, let's zoom back out to the 30,000-foot view. What we've seen is that NumPy isn't just another library you can use. It is the strategic computational engine that powers the entire modern data science and AI world.
I mean, just think of the titans of the Python ecosystem. Pandas for data analysis, scikit-learn for machine learning, even TensorFlow for deep learning. What do they all have in common? Every single one of them is built directly on top of NumPy. The NumPy array as the high-performance bedrock that makes all of their amazing features possible. So we'll end with a strategic question for you to take back to your teams. Is your computational architecture an asset that's enabling you to move faster and get real-time insights? Or is it a hidden liability secretly slowing you down? Because in today's market, that choice makes all the difference.